In early 2014, the esteemed physicist Roger Penrose, then 82 years old, co-authored a paper that sent ripples through the fields of physics, biology, and philosophy. It was a bold defense of a theory he had been developing since the 1980s with an anesthesiologist named Stuart Hameroff. The theory, called Orchestrated Objective Reduction, or OR, proposed something radical. It suggested that human consciousness is not a product of classical computation between neurons. Instead, it arises from quantum processes happening inside the brain's smallest structures, tiny protein cylinders called microtubules. And Penrose argued that these microtubules could sustain a delicate quantum state, a form of coherent superposition, before a moment of objective reduction occurred. This wasn't just a random collapse of the quantum wave function, but a specific physical process tied to the fundamental geometry of spacetime. In essence, each moment of conscious awareness was a tiny quantum computation, a choice made by the universe itself happening inside our heads. The theory directly linked the mystery of the mind to the deepest, most bizarre rules of reality. It implied our very thoughts were woven into the quantum fabric of the cosmos. Most of the scientific community was, and remains, deeply skeptical. The brain is considered too warm, wet, and noisy an environment for such delicate quantum effects to last for any meaningful time. Yet, the OR theory persists because it addresses a profound unease. Why does a universe of mindless particles and empty space produce minds that can ponder it? Penrose's idea, whether right or wrong, points to a deeper question. Does the universe just happen to allow for consciousness, or is there something in its basic code, its physical laws and constants, that points toward it? This leads us to the Anthropic principle. The principle, in its simplest form, states that the universe we observe must be one that allows observers to exist. It's a kind of selection bias. If the universe were different, we wouldn't be here to notice. But this simple statement hides a series of cosmic coincidences so profound they challenge our understanding of reality. The laws of physics seem to be balanced on a knife's edge. A tiny nudge in any number of fundamental values would result in a universe that is sterile and dead. A cosmos without stars, without chemistry, without planets, without life. It seems the universe is not just habitable, but suspiciously well suited for us. Number 17, the universe's expansion, is not just right. It's bizarrely precise. The greatest mismatch between theory and observation in all of science is a factor of 1 followed by 120 zeros. In 1998, 2 separate teams of astronomers studying distant supernovae made a startling discovery. They found the expansion of the universe, which began with the Big Bang 13.8 billion years ago, is not slowing down due to gravity, as everyone expected. It is speeding up. The culprit was dubbed dark energy, an unknown repulsive force inherent to the fabric of space-time itself. This force is represented by a number called the cosmological constant. Albert Einstein had first proposed this constant in 1917 to make his equations of general relativity describe a static, unchanging universe, which was the prevailing view at the time. When Edwin Hubble discovered the universe was expanding in 1929, Einstein reportedly called the constant his biggest blunder. But the 1998 discovery brought it back. The problem is the number's value. Our best theories of quantum physics predict a value for this energy of empty space. That predicted value is 10 raised to the power of 120 times larger than the value we actually observe. This is a discrepancy so vast it has no parallel in science. It's like measuring the width of North America and being off by a distance larger than the entire observable universe. The value we see is not 0, but it is extraordinarily close to it, and this precise tiny value is crucial for our existence. If the cosmological constant were as large as theory predicts, its repulsive force would have been overwhelming. It would have ripped the nascent universe apart in the first fractions of a second. Matter would never have had a chance to clump together under gravity. No galaxies, no stars, no planets, and no people would have ever formed. The universe would be an endlessly expanding, cold, thin vapor of particles. If the constant had a similarly large but negative value, it would have acted like an extra source of gravity. The universe would have expanded for a moment and then immediately collapsed back on itself in a big crunch long before the first star could ignite. Life requires a universe that is old and stable. It needs billions of years for stars to form, create heavy elements, and then for planets to coalesce and for complex chemistry to emerge. This requires a delicate balance between the outward push of dark energy and the inward pull of gravity. The observed value of the cosmological constant sits in an exquisitely narrow window that allows for exactly this. It's small enough to let gravity dominate on smaller scales to build galaxies, but just large enough to be detectable on the cosmic scale. The universe seems tuned to expand at a Goldilocks rate. Not too fast, not too slow. Just right for structures to form and for time to pass. The anthropic explanation is straightforward. In a hypothetical multiverse with countless universes, the cosmological constant would have a different random value in each one. The vast majority of these universes would be sterile, either ripping themselves apart or collapsing instantly. We, by definition, find ourselves in one of the very rare universes where the value is just right for us to be here and ask the question. We won the cosmic lottery. But to many physicists, this feels like an unsatisfactory answer. It replaces a problem of fine-tuning with the untestable hypothesis of an infinite number of other universes. It doesn't explain why the number is what it is. It just says that in a big enough lottery, even unlikely numbers get picked. The fact remains that the energy of empty space, the most abundant energy in the cosmos, has a value that appears absurdly fine-tuned for our existence. Number 16, the strong nuclear force, is tuned for atomic stability. Inside the nucleus of every atom, protons and neutrons are bound together by the strongest of nature's four fundamental forces, the strong nuclear force. This force is about 137 times stronger than electromagnetism, the force that makes positively charged protons want to fly apart. It operates only over incredibly short distances, essentially the width of an atomic nucleus. Its strength is what makes stable atoms possible, but its strength is also a finely tuned parameter. If the strong force were just 2% stronger, protons would be able to fuse together much more easily. In the early universe, this would have meant that almost all the hydrogen would have been fused into heavier elements. Specifically, it would create diprotons, helium-2 nuclei, which would be stable. In our universe, diprotons are not stable, which allows for a slow, steady chain of nuclear fusion in stars. With a slightly stronger force, all the hydrogen fuel of the universe would have been burned up in the first few minutes after the Big Bang. Stars, as we know them, long-lived, stable fusion reactors, would never exist. The sun would not shine. Without hydrogen, there is no water, a molecule essential for life as we know it. The universe would be composed almost entirely of helium and heavier elements with no long-term energy source to power complex systems. Conversely, if the strong force were about 5% weaker, its grip would not be enough to overcome the electromagnetic repulsion between protons. In deuterium, a nucleus made of one proton and one neutron would not be stable. Deuterium is a crucial stepping stone in the fusion process that powers stars. Without stable deuterium, stars would not ignite. The universe would be filled with nothing but hydrogen. No fusion means no heavier elements, no carbon, no oxygen, no nitrogen, no iron. The periodic table would stop at hydrogen. A universe made of only hydrogen cannot support chemistry, let alone biology. There would be no planets, no rocks, no life. The strength of the strong force is in a narrow band that allows for both the existence of hydrogen, the fuel of stars, and the process of stellar nucleosynthesis, the forging of heavier elements. It permits a universe that is both dynamic and stable, a universe that can build complexity over billions of years. This value is determined by a fundamental physical constant called the strong coupling constant. We do not have a theory that explains why this constant has the value it does. It is simply a number that we measure in experiments. The Anthropic principle suggests we observe this value because any other value would lead to a universe in which we could not exist. The delicate balance allows for a rich and complex chemistry. It allows stars to burn for billions of years, providing the energy needed for life to evolve on orbiting planets. It's another fundamental number in the cosmic recipe that seems tailored for a universe that can create observers. Number 15, the weak nuclear force controls the sun's fuel and elements. The weak nuclear force is the odd one out among the four fundamental forces. As its name suggests, it is much weaker than the strong force and electromagnetism. It also operates over even shorter distances than the strong force. Its primary role involves radioactive decay and interactions with tiny elusive particles called neutrinos. It might seem like a minor player, but without its specific strength, the universe would be a sterile place. The weak force's most important job for life is mediating the very first step of the proton-proton chain reaction, the main fusion process in stars like our sun. This step involves two protons fusing. One of them must transform into a neutron, releasing a positron and a neutrino. This transformation of a proton into a neutron is governed by the weak force. The key is that this process is incredibly slow and inefficient. The weak force makes it a very low probability event. This is why the sun burns its hydrogen fuel so slowly and steadily. It has been burning for 4.6 billion years and has enough fuel for another 5 billion. If the weak force were significantly stronger, this proton to neutron conversion would happen much more easily and quickly. Stars would burn through their hydrogen fuel at a furious rate. Instead of lasting for billions of years, they would exhaust their fuel in a few million years or less. This is not nearly enough time for a planet to cool, for an atmosphere to form, and for the slow process of evolution to produce complex life. Our sun would have burned out long before the first multicellular organisms appeared on Earth. The universe would be full of short-lived, intensely hot stars with no stable, long-term energy sources. If the weak force were much weaker, the conversion of protons to neutrons would be too rare. The initial step of stellar fusion would not happen at all. Stars would not ignite. The universe would be a dark collection of hydrogen and helium clouds, never forming the heavier elements necessary for life. The specific strength of the weak force also plays a crucial role in the creation of these heavy elements. When massive stars run out of fuel, they collapse and explode in a supernova. And during this cataclysmic event, the weak force is essential. It governs the interactions that release a massive burst of neutrinos. This neutrino burst carries away most of the explosion's energy and is responsible for blowing the star's outer layers into space. These layers are rich with the heavy elements forged in the star's core. The explosion seeds the galaxy with elements like carbon, oxygen, iron, and all the others needed to form rocky planets and living organisms. If the weak force were different, supernovae would not happen in the way they do. The heavy elements would remain trapped in the dead stellar cores, like white dwarfs or neutron stars. The cosmos would be impoverished, unable to build the chemical complexity life requires. The weak force, therefore, acts as a cosmic regulator. It sets the pace of stars, ensuring they burn long and steady, and it ensures that when they die, their life-giving elements are recycled back into the cosmos. Like the other forces, its value is a fundamental constant of nature that we measure but cannot derive from first principles. It just happens to be the right strength to allow for a universe with long-lived stars and a rich periodic table. Number 14, gravity's faintness is the reason anything large exists. Gravity is the most familiar of the four forces, yet it is by far the weakest. it is astonishingly feeble. The electromagnetic force between two protons in an atomic nucleus is about 10 raised to the power of 36 times stronger than the gravitational force between them. A simple refrigerator magnet holding up a piece of paper demonstrates this. The tiny magnet's electromagnetic force easily overcomes the gravitational pull of the entire planet Earth. The extreme weakness of gravity is essential for the existence of a large, long-lived, and structured universe. If gravity were significantly stronger, say a trillion times stronger, still incredibly weak compared to the other forces, the universe would be a very different place. Stars would form much more quickly and from much smaller clouds of gas. They would be far smaller than our sun, perhaps only a millionth of its mass. These tiny stars would burn through their fuel in a flash, lasting perhaps only a few thousand years. They would radiate energy so intensely that any nearby planet would be sterilized. The intense gravity would also mean that galaxies would be much smaller and more densely packed. The universe would be a chaotic place of frequent collisions and disruptions. There would be no stable, long-lasting planetary systems. On the largest scales, a much stronger gravitational force would have caused the universe to stop expanding and collapse back on itself long ago. There simply would not have been enough time for cosmic evolution. Life, which appears to require billions of years of stability, would have no chance. If gravity were even weaker than it is, it would be too inefficient at pulling matter together. Gas clouds would struggle to collapse under their own weight. Star formation would be slow and rare, or might not happen at all. Galaxies might never form, with matter remaining as a diffuse, evenly spread gas. Without stars, the universe would remain dark and cold, composed only of the light elements created in the Big Bang. No heavy elements, no heat, no energy sources. The observed strength of gravity, defined by the gravitational constant G, allows for a universe that is structured on a vast hierarchy of scales. It is weak enough to allow the universe to expand for billions of years, giving time for complexity to develop. It is strong enough to pull matter together to form immense galaxies, but not so strong that it crushes everything into a chaotic mess. It allows for the formation of stars that are large enough to burn for billions of years, but not so large that they burn out instantly. This juiced right, strength of gravity is a fundamental property of our universe. It dictates the scale and pace of cosmic history. A slight change in its value would result in a cosmos that is either a fleeting fireball or a dark, empty void. The anthropic view is that we live in a universe with a weak gravity because universes with strong gravity don't last long enough to produce observers. Number 13, the laws of electromagnetism are perfect for chemistry and light. Electromagnetism is the force responsible for almost everything we experience in our daily lives. It holds atoms together. It governs all of chemistry. It is the force behind light, radio waves, and electricity. Its properties are determined by several constants, most notably the fine structure constant, often represented by the Greek letter alpha A. This number, approximately 137, dictates the strength of the electromagnetic interaction. Like the other fundamental constants, its value appears to be exquisitely tuned, and if the fine structure constant were slightly different, the universe would be unrecognizable. For example, a change of just a few percent would dramatically alter stellar fusion. The stability of atomic nuclei depends on a delicate balance between the repulsive electromagnetic force between protons and the attractive strong nuclear force. Altering electromagnetism would shift this balance, making it impossible for stars to create carbon and oxygen, the building blocks of life. But the effects on chemistry would be even more direct. The fine structure constant determines the size of atoms and the strength of chemical bonds. If it were larger, electrons would be held more tightly to the atomic nucleus. This would make chemical bonds much stronger and more rigid. And complex molecules like DNA, which need to be able to flex, unzip, and replicate, might be too stiff to function. Life relies on a certain floppiness in its molecular machinery. If the constant were smaller, electrons would be held more loosely. Chemical bonds would be weaker. This could mean that complex molecules essential for life would fall apart at normal temperatures. The delicate structures of proteins would not hold their shape. A universe with weaker electromagnetism might be a place where only the simplest molecules could exist, and only at very low temperatures. Beyond chemistry, electromagnetism governs the nature of light. The energy of photons produced by atomic transitions is proportional to the square of the fine structure constant. The fact that stars produce light in the visible spectrum and that water is transparent to this light is a consequence of the value of this constant. If it were different, stars might produce only high energy gamma rays or low energy radio waves. A water-based atmosphere on a planet might be opaque, preventing starlight from reaching the surface to drive photosynthesis. The universe seems to have a specific transparency window that allows energy from a star to power biology on a planet. The very existence of stable atoms with distinct electron shells, the foundation of the periodic table, and all of chemistry is a result of the balance set by electromagnetism. Or a universe without these properties would be a universe without structure, without communication, without the complex interplay of molecules that we call life. The value of 137 is one of the great mysteries of physics. We have no theory that explains it. It appears to be a pure dimensionless number that just happens to have the value it does. And that value happens to be perfect for a universe filled with complex chemistry and powered by starlight. Number 12, the tiny mass difference between a proton and a neutron. A proton and a neutron are the two building blocks of atomic nuclei. They are very similar in mass, but not identical. A neutron is slightly heavier than a proton by about 0.14%. This tiny sliver of a difference has profound consequences for the universe. Because a free neutron is heavier than a proton, it is unstable. A lone neutron will decay into a proton, an electron, and an antineutrino with a half-life of about 10 minutes. A proton, being the lighter of the two, is stable. It does not decay. This stability is the reason matter exists at all. Now, consider a universe where the neutron was slightly lighter than the proton. In this scenario, protons would be the unstable particles. They would decay into neutrons, positrons, and neutrinos. The hydrogen atoms, which consist of a single proton and an electron, would not be stable. Within minutes of the Big Bang, all the protons in the universe would have decayed into neutrons. The cosmos would be filled with neutrons and other particles. There would be no hydrogen atoms. No hydrogen means no stable stars like our sun, which are powered by fusing hydrogen. It means no water H2O. It means no organic chemistry, which is based on hydrocarbons. It would be a universe of neutron stars and black holes with no possibility for the kind of chemistry that life requires. The universe would be dead on arrival. Now, what if the mass difference were larger than it is? What if the neutron were, say, 1% heavier than the proton instead of just 0.14%? This would have drastically affected the production of elements in the Big Bang. During the first few minutes of the universe's existence, a process called Big Bang nucleosynthesis created the first light elements. The ratio of protons to neutrons was set when the universe was about 1 second old. A larger mass difference would have tipped the scales heavily in favor of protons. Far fewer neutrons would have been available to form deuterium and then helium. The universe would have emerged from this early phase with almost 100% hydrogen. While this might sound good for creating stars, it would mean very little helium was produced. The way heavier elements are made in stars depends on the initial mix of hydrogen and helium. The stellar processes would be altered in ways that could make the production of elements like carbon much more difficult. The slight mass difference we observe allows for a universe with about 75% hydrogen and 25% helium coming out of the Big Bang. This is the perfect starting mixture for the cosmic furnace. It leads to the formation of long-lived stars and the efficient production of the entire periodic table of elements inside them. This mass difference is a result of the masses of the up and down quarks that make up protons and neutrons, and the binding energy of the strong force. The values of these quark masses are, like the other constants, fundamental parameters of the standard model of particle physics. We do not know why they have the values they do, but a tiny tweak in these values would have resulted in a universe where either matter was unstable or the elemental building blocks for life were never forged. Number 11, the impossible coincidence that creates carbon. All life on Earth is carbon-based. Carbon's ability to form 4 stable bonds allows it to create the long, complex chains and rings that are the backbones of organic molecules like DNA and proteins. But the existence of abundant carbon in the universe is the result of an astronomical coincidence, a fact that deeply troubled the astrophysicist Fred Hoyle in the 1950s. Hoyle was working on the problem of how elements heavier than helium are created in stars. The process, called stellar nucleosynthesis, involves fusing lighter nuclei together. The obvious pathway to carbon, which has 6 protons and 6 neutrons, would be to fuse 3 helium-4 nuclei, 2 protons, 2 neutrons each. The problem is that fusing 3 things at once is a very unlikely event. The more plausible pathway would be a 2-step process. First, 2 helium-4 nuclei fuse to create a beryllium-8 nucleus, 4 protons, 4 neutrons. Then, this beryllium-8 nucleus is struck by a 3rd helium-4 nucleus to form carbon-12. The major roadblock is that beryllium-8 is incredibly unstable. It has a half-life of just 10, raised to the power of 17 seconds. It decays almost instantly back into 2 helium nuclei. For a 3rd helium nucleus to hit it in that fleeting moment seemed impossible. There wouldn't be nearly enough carbon produced to account for the amount we see in the universe and in ourselves. Hoyle realized that for this process to work efficiently, there must be a resonance. A resonance is a state where the energies of the colliding particles match an excited energy level of the nucleus they are forming. This makes the reaction vastly more likely. Hoyle predicted, based on the sheer necessity of our existence, that the carbon-12 nucleus must have an excited state with an energy of very close to 7.65 million electron volts MeV. This would be just above the combined energy of a beryllium-8 nucleus and a helium-4 nucleus. He went to a group of nuclear physicists at Caltech led by William Fowler and urged them to look for this undiscovered energy level in carbon-12. They were skeptical, but eventually, ran the experiment. To their astonishment, they found the excited state exactly where Hoyle predicted it would be. This is now known as the Hoyle state, but the coincidence doesn't end there. For carbon to be abundant, it must be created, but it must not be easily destroyed. The next step in the fusion chain is for a carbon-12 nucleus to capture another helium-4 nucleus to become oxygen-16. If there were a strong resonance for this reaction as well, almost all the newly formed carbon would be immediately converted into oxygen. Life needs both carbon and oxygen. It turns out that the relevant energy level in oxygen-16 is at 7.12 MeV, just below the combined energy of carbon-12 and helium-4. This makes the reaction possible, but not too efficient. It proceeds at a moderate rate, leaving behind significant amounts of both carbon and oxygen. So we have a double coincidence. One nuclear resonance is precisely tuned to boost the production of carbon, and another is precisely detuned to prevent that same carbon from being quickly destroyed. The result is a universe rich in both elements. Hoyle himself was deeply shaken by this discovery. He later wrote, A common sense interpretation of the facts suggests that a super intellect has monkeyed with physics, as well as with chemistry and biology, and that there are no blind forces worth speaking about in nature. The energy levels of atomic nuclei are determined by the complex interplay of the strong and electromagnetic forces. A slight change in the strength of either of these forces would shift these resonance levels. And if they shifted, the universe would have almost no carbon, or no oxygen, or both. The anthropic explanation is that in a multiverse, we simply inhabit one of the rare universes where the laws of physics permit the Hoyle state to exist, making our kind of life possible. Number 10, water is a cosmic anomaly designed for life. Water is so common on Earth that we take its properties for granted, but chemically, water H2O is one of the strangest substances in the universe. Its weird properties are not just incidental, they appear to be essential for the existence of complex life. Most substances become denser as they get colder. Water does too, but only down to 4 degrees Celsius. Below that, as it approaches its freezing point, it starts to expand and become less dense. This is why ice floats. This single anomalous property is crucial for life on Earth. If ice were denser than water, it would sink. In winter, lakes and oceans would freeze from the bottom up. Year after year, the ice would accumulate until eventually entire bodies of water were frozen solid, killing almost all aquatic life. Instead, a layer of floating ice forms on the surface, insulating the liquid water below and allowing life to survive the winter. This property stems from the shape of the water molecule and the nature of its hydrogen bonds. Water is a polar molecule. The oxygen atom has a slight negative charge, and the 2 hydrogen atoms have a slight positive charge. This allows water molecules to stick to each other through hydrogen bonds. As water freezes, these bonds arrange the molecules into a rigid, open lattice crystal structure that takes up more space than the jumbled molecules in liquid water. Water also has an incredibly high specific heat capacity. This means it can absorb a lot of heat energy without its own temperature increasing very much. This property allows large bodies of water, like oceans, to act as giant thermal regulators for the planet. They absorb heat in the summer and release it slowly in the winter, moderating global climates and preventing extreme temperature swings that would be hostile to life. Its high heat of vaporization also means it takes a lot of energy to evaporate water. This is the basis for cooling through perspiration in many animals. Water is often called the universal solvent because its polarity allows it to dissolve more substances than any other liquid. This is vital for life. It means that water can transport nutrients, minerals, and dissolved gases within living organisms and ecosystems. The blood in our veins, the sap in trees, and the water in our cells all rely on this solvent property to carry the chemical building blocks of life. Furthermore, water has high surface tension, the second highest of all liquids. This allows water to be pulled up through the narrow xylem tubes in plants, defying gravity to bring water from the roots to the leaves. All these unique properties, ice floating, high heat capacity, excellent solvent, high surface tension, arise from the fundamental laws of quantum mechanics and electromagnetism as they apply to a simple 3-atom molecule. Yet, this one substance seems to possess a whole suite of features that are not just beneficial, but seemingly essential for the kind of stable planetary scale biology we see on Earth. It's a remarkable convergence of physical properties in a single abundant molecule that makes it the perfect medium for life. Number 9, carbon's unique chemistry is the basis for complexity. Life is a phenomenon of complexity. To build the intricate machinery of a cell, you need an element that can act as a versatile and stable scaffold. That element is carbon. The entire field of organic chemistry is the study of carbon compounds, a field so vast it dwarfs the chemistry of all other elements combined. Carbon's special status comes from its atomic structure. It has 4 electrons in its outer shell, which means it can form 4 strong covalent bonds with other atoms. This tetravalent bonding allows it to create a huge variety of structures. It can form long, stable chains, polymers like plastics and starches, branch chains, and complex rings like benzene or the bases in DNA. No other element comes close to this versatility. Silicon is just below carbon in the periodic table and also has 4 valence electrons. For this reason, science fiction has often speculated about silicon-based life. However, silicon has several major drawbacks. Silicon bonds are significantly weaker than carbon bonds. This makes long silicon chains much less stable. They tend to break down easily. Silicon also has a strong affinity for oxygen. When carbon is oxidized during metabolism, it forms carbon dioxide CO2, a gas. This makes it easy for an organism to expel as waste. When silicon is oxidized, it forms silicon dioxide SiO2, which is essentially sand or quartz. It is difficult to imagine a life form that has to excrete tiny grains of sand as a waste product. The energy required to break down solid SaO2 would be immense, making a silicon-based metabolism far less efficient. The stability of carbon bonds allows for the creation of gigantic information-rich molecules like DNA. A single human DNA molecule can contain billions of atoms, storing the blueprint for an entire organism in a stable, readable format. Carbon's ability to bond with other elements like hydrogen, oxygen, nitrogen, phosphorus, and sulfur creates an even wider array of chemical possibilities, giving rise to the functional groups that define amino acids, sugars, and lipids. The universe is not short of other elements. Hydrogen and helium make up over 98% of the atomic matter. Oxygen is the 3rd most abundant. Yet, life is not based on these. It is based on carbon, which is only the 4th most abundant element. The reason is chemistry. The laws of quantum mechanics, which dictate the rules of chemical bonding, give carbon a unique and privileged role. Its properties are not just a little better than other elements, they are orders of magnitude more suitable for building complex, stable, and varied molecular structures. The anthropic argument here is that the very rules of chemical bonding seem to favor carbon in a way that is highly conducive to life. If the quantum rules were different, perhaps no element would have this unique combinatorial power. That of a universe without an element like carbon would likely be a universe without complexity and therefore without life. Number 8, 3 dimensions of space are a prerequisite for stability. We live in a universe with 3 spatial dimensions: length, width, height, and 1 time dimension. This seems so fundamental that we rarely question it, but why not 2 spatial dimensions, or 4, or 10? Theoretical physics, particularly string theory, often posits the existence of extra hidden dimensions. But for a universe to support life as we know it, 3 large spatial dimensions seem to be a strict requirement. Consider a universe with only 2 spatial dimensions, like the surface of a table. In such a flatland, the possibilities for complexity are severely limited. For example, a digestive tract that goes all the way through an organism would cut it in 2. The rules of topology in 2D are much more restrictive. Neural networks would be difficult to construct without wires crossing, which would be impossible in a purely 2D plane. The laws of physics would also be different. Gravity in a 2D universe would not follow an inverse square law. Orbits would not be stable in the same way. It is highly doubtful that stable planetary systems could form. Now, consider a universe with 4 or more spatial dimensions. Here, the problems are even more severe. The physicist Paul Ehrenfest showed in 1917 that in any dimension greater than 3, stable orbits under an inverse square law like gravity or electromagnetism are impossible. An inverse square law arises naturally in 3 dimensions because the surface area of a sphere increases with the square of its radius. In 4 dimensions, the force of gravity would follow an inverse cube law. This means that the gravitational pull would change much more dramatically with distance. Any tiny perturbation in a planet's orbit would send it either spiraling into its star or flying off into space. There would be no stable solar systems. The same instability would apply to the orbits of electrons in atoms. In a 4D universe, electrons would either spiral into the nucleus or escape the atom entirely. Stable atoms, the basis of all chemistry, could not exist. The very structure of matter would collapse. The propagation of waves would also be fundamentally different. In 3D, when you create a disturbance like a sound or a light pulse, it travels outward as a clean spherical wave. Once the wave passes, things return to normal. In dimensions other than 3 specifically, in any odd number of dimensions greater than 1, waves would be messy. A pulse would leave behind a wake that continues to reverberate. This would make any kind of reliable signal processing or information transfer impossible. A nerve impulse or a radio signal would be hopelessly blurred and distorted. 3 dimensions appear to be the unique sweet spot. It is complex enough to allow for intricate structures and networks like brains and ecosystems, yet it is simple enough to allow for stability and predictability in physical laws like gravity and atomic structure. It permits stable orbits and clean signal propagation. Life depends on both complexity and stability. The fact that our universe has exactly 3 large spatial dimensions seems to be another one of these prerequisite conditions for the existence of observers. If the number of dimensions were a variable in some grander multiverse, only the 3D universes would be capable of producing beings who could ponder the question. Number 7. The universe contains a little bit of matter, and that's everything. According to our best physical theories, the Big Bang should have produced matter and antimatter in exactly equal amounts. Matter is the stuff we are made of: protons, neutrons, electrons. Antimatter is its mirror image: antiprotons, antineutrons, positrons. They have the same mass, but opposite charge. When a particle of matter meets its antiparticle, they annihilate each other in a burst of pure energy. If the early universe had contained perfect symmetry between matter and antimatter, their fate would have been sealed. In the first second after the Big Bang, as the universe cooled, all the matter and antimatter would have found each other and annihilated. The result would have been a universe filled with nothing but photons, light, and perhaps some neutrinos. There would be no matter left over to form stars, galaxies, planets, or people. The universe would be a vast, empty, sterile bath of radiation. But this is not what we see. We live in a universe made overwhelmingly of matter. For every galaxy we see, there is not an anti-galaxy made of antimatter. The entire cosmos seems to be built from one type of stuff. This means there must have been an imbalance or an asymmetry in the early universe. For some reason, for every billion pairs of matter and antimatter particles, there was one extra particle of matter. After all the annihilation was over, that tiny leftover fraction, 1 part in $1 billion, is what formed everything we see today. You, the Earth, the Sun, the Milky Way galaxy, all of it is the result of that slight cosmic imbalance. The question is, where did this asymmetry come from? The Russian physicist and dissident Andrei Sakharov laid out the necessary conditions for this to happen in 1967. They involve a violation of a fundamental symmetry of physics called CP symmetry, charge parity symmetry, and processes that occurred out of thermal equilibrium. Experiments in particle accelerators have confirmed that some subatomic particles do indeed violate CP symmetry, but the amount of violation we have measured so far is not nearly enough to explain the huge observed asymmetry of matter in the cosmos. It remains one of the biggest unsolved problems in physics. We exist because of a fundamental flaw, a slight imperfection in the laws of physics that favored matter over antimatter. If the symmetry had been perfect, we would not be here. If the asymmetry had been much larger, perhaps the universe would be so dense with matter that it would have collapsed back on itself. The observed amount, a tiny preference for matter, seems to be just right to produce a universe with the density and composition we observe. The Anthropic principle offers a perspective. If the universe weren't built from this leftover matter, no observers would exist to notice the missing antimatter. Our very presence is evidence of this primordial imbalance. It's a profound thought The entire material universe is essentially a rounding error in a cosmic cataclysm of annihilation. Number 6, our sun is an uncommonly quiet and stable star. The sun is the engine of life on Earth, providing a steady and reliable stream of energy. We tend to think of it as a typical star, but in many ways it is quite special. The sun is a G-type main sequence star, also known as a yellow dwarf. These stars are relatively rare. About 75% of the stars in the Milky Way are M-type red dwarfs. These are much smaller, cooler, and dimmer than the sun. While they have extremely long lifespans, trillions of years, they present serious problems for habitability. Red dwarfs are notoriously volatile, especially in their youth. They can produce powerful stellar flares, blasts of radiation that can be hundreds or thousands of times more powerful than the sun's. A planet orbiting in the habitable zone of a red dwarf would be very close to the star, making it extremely vulnerable to these flares. Such a flare could strip away the planet's atmosphere and bathe its surface in sterilizing X-rays. These stars also emit most of their light in the red and infrared parts of the spectrum, which is less efficient for photosynthesis as we know it. On the other end of the scale are the large, bright blue O-type and B-type stars. These stars are even rarer than G-type stars. They are massive and hot, but they burn through their fuel at a furious pace. Their lifespans are measured in millions of years, not billions. This is almost certainly not enough time for complex life to evolve. The sun is in a sweet spot. It is massive enough to have a stable, habitable zone far enough out to reduce the dangers of flares and tidal locking, where a planet always shows the same face to its star. Yet, it is small enough to have a lifespan of about 10 billion years, giving life a long, stable period in which to develop. Our sun is also unusually stable even for a G-type star. Studies of similar stars have shown that many of them are much more variable, with more frequent superflares and changes in brightness. The sun's output is remarkably constant, varying by only about 0.1% over its 11-year solar cycle. This stability has been crucial for maintaining a stable climate on Earth over geological timescales. Furthermore, the sun's location in the Milky Way is also fortunate. It resides in the galactic habitable zone. It is far enough from the galactic center to avoid the intense radiation and gravitational disruptions common there. Yet it is close enough to the center to be in a region with a sufficient concentration of heavy elements, the elements forged in earlier generations of stars, which are necessary to form rocky planets. A star's composition, its size, its stability, and its location all must fall within a narrow range to be suitable for hosting a planet with life. Our sun seems to check all the boxes. While there are billions of G-type stars in our galaxy, the combination of stability and a well-behaved planetary system like our own might be much rarer than we think. Number 5, Earth's magnetic field is a non-negotiable life support system. Life on Earth exists under the protection of an invisible shield, the planetary magnetic field. This field is generated by the motion of molten iron in the Earth's outer core, a process known as a geodynamo. It extends far out into space, creating a region called the magnetosphere. This shield is not a luxury, it is an absolute necessity for life on a planet with an atmosphere. The sun is constantly emitting a stream of charged particles called the solar wind. This wind travels through space at hundreds of kilometers per second. Without the magnetosphere, the solar wind would slam directly into Earth's upper atmosphere. Over millions of years, it would strip away the atmosphere, particularly lighter gases like water vapor. This is what is believed to have happened to Mars. Mars once had a thicker atmosphere and liquid water on its surface, but its geodynamo shut down billions of years ago. Without a protective magnetic field, the solar wind eroded its atmosphere, turning it into the cold, dry desert world it is today. The magnetic field also protects life on the surface from harmful cosmic rays. These are high-energy particles, mostly protons, that originate from supernova and other violent events across the galaxy. They travel at nearly the speed of light. When they strike living tissue, they can damage DNA, causing mutations and cancer. The magnetosphere deflects the vast majority of these cosmic rays, funneling them toward the poles, where they create the auroras. The strength and stability of Earth's magnetic field are crucial. It needs to be strong enough to stand up to the solar wind and the occasional powerful solar storm. The fact that Earth has maintained a significant magnetic field for at least 3.5 billion years is remarkable. It requires a planet of a certain size and composition. It needs a liquid outer core, a solid inner core, and a sufficient rate of rotation to drive the dynamo. Venus, our so-called Hister planet, is similar in size but rotates very slowly. One Venusian day is longer than its year and lacks a significant magnetic field. This lack of a shield is one reason its atmosphere has evolved so differently, becoming a runaway greenhouse inferno. The existence of a long-lasting, stable geodynamo is likely a critical filter for planetary habitability. It is not something that can be taken for granted. It depends on the specific history of a planet's formation, its size, and its internal heat engine. The anthropic principle suggests that we find ourselves on a planet with a strong magnetic field, because planets without one are not suitable for the long-term survival of a biosphere and the evolution of observers. Our invisible shield is another piece of the puzzle, a feature that makes our world a rare and protected cradle for life. Number 4, the moon is not just a nightlight, it's Earth's stabilizer. Earth has a moon that is unusually large compared to its parent planet. The moon's diameter is about 27% of Earth's. No other planet in our solar system has a satellite that is so large in proportion to itself. Pluto and Charon are a closer pair, but Pluto is a dwarf planet. This large moon is not just a pretty object in the night sky. It plays a critical role in making Earth a stable and habitable planet. Its most important function is stabilizing Earth's axial tilt, or obliquity. The Earth is tilted on its axis by about 23.5 degrees. This tilt is what gives us our seasons. The gravitational pull of our large moon acts like a giant anchor, preventing this tilt from varying wildly over time. Without the moon, the gravitational tugs from other planets, especially Jupiter, would cause Earth's axial tilt to wobble chaotically. It could swing from nearly 0 degrees no seasons to as much as 85 degrees extreme seasons where the poles point almost directly at the sun. Such drastic shifts occurring over timescales of millions of years would lead to catastrophic changes in climate. Imagine a world where the North Pole points toward the sun for months on end, creating an unimaginably hot summer, while the other hemisphere freezes. A stable climate over geological time has been essential for the slow, continuous process of evolution. The moon provides this stability. Mars, with its 2 tiny moons, Phobos and Deimos, has no such anchor. Its axial tilt is known to have varied dramatically from 15 to 35 degrees, which has likely contributed to major climate shifts throughout its history. The moon also contributes to Earth's tides, the twice daily rise and fall of the oceans caused by the moon's gravity created vast intertidal zones. Many biologists believe these zones, with their regular cycle of wet and dry conditions, may have been the perfect laboratory for life to make the transition from the sea to the land. The tides also help to mix ocean water, circulating heat and nutrients around the globe. The prevailing theory for the moon's origin is the giant impact hypothesis. It suggests that early in the solar system's history, a Mars-sized object named Theia collided with the proto-Earth. The cataclysmic impact threw a vast amount of debris into orbit, which eventually coalesced to form the moon. This was a chance event. If the impact had been slightly different, a different angle, a different speed, like it might have shattered the Earth completely, or the debris might have failed to form a moon. The existence of our large stabilizing moon is the result of a specific, violent, and contingent event in our planet's past. It is another factor that makes the Earth system so uniquely suited for life. A planet needs more than just the right distance from its star. It appears to need a specific kind of planetary system architecture, and for Earth, that includes a giant companion. Number 3, plate tectonics acts as a planetary thermostat. The surface of the Earth is not a single solid shell. It is broken up into large, rigid plates that are constantly in slow motion, floating on the semi-molten mantle beneath. This process, plate tectonics, is responsible for earthquakes, volcanoes, and the formation of mountain ranges. It is also a critical component of Earth's long-term climate stability, acting as a planetary thermostat through a process called the carbonate-silicate cycle. Here is how it works. Carbon dioxide CO2 in the atmosphere dissolves in rainwater, forming a weak carbonic acid. This acid rain falls on the land and erodes silicate rocks. The chemical reaction pulls CO2 out of the atmosphere and turns it into carbonate minerals, which are then washed into the oceans. In the oceans, marine organisms use these minerals to build their shells and skeletons. When they die, they sink to the seafloor, forming layers of carbonate rock like limestone. This process effectively locks away atmospheric CO2 in the Earth's crust. If this were the only process, all the CO2 would eventually be removed from the atmosphere, and the Earth would freeze. This is where plate tectonics comes in. Through the process of subduction, the seafloor crust, carrying its load of carbonate sediments, is slowly dragged down into the hot mantle at the boundary of tectonic plates. The heat and pressure in the mantle cook the rocks, releasing the CO2. This CO2 is then vented back into the atmosphere through volcanic eruptions. This completes the cycle. This cycle has a built-in feedback mechanism that stabilizes the climate. If the Earth gets too cold, rainfall decreases, which slows down the erosion of rocks. But volcanic activity continues pumping CO2 into the atmosphere. The CO2 level rises, the greenhouse effect strengthens, and the planet warms up. If the Earth gets too hot, rainfall and erosion increase, which pulls more CO2 out of the atmosphere. This reduces the greenhouse effect and the planet cools down. This geological carbon cycle acts as a thermostat over timescales of hundreds of thousands of years, keeping Earth's climate in a range suitable for liquid water and life. Plate tectonics is not a guaranteed feature of a rocky planet. It requires a planet to be a certain size to retain enough internal heat to keep the mantle convecting. It needs the right amount of water to lubricate the plate boundaries. Venus, for example, is about the same size as Earth, but appears to have no active plate tectonics, possibly because it lost its water. Mars is smaller and has cooled off, its geology now largely dormant. The fact that Earth has maintained active plate tectonics for billions of years is another key feature that sets it apart. It is a dynamic, living planet recycling its crust and regulating its atmosphere. This deep geological process is intimately linked to the long-term habitability of our world. Number 2, the universe started with extremely low entropy. The second law of thermodynamics states that the total entropy, or disorder, of a closed system always increases over time. Things fall apart, order degrades into chaos. A hot cup of coffee cools down, a neat pile of sand spreads out, an egg cannot be unscrambled. This law defines the arrow of time, the reason we remember the past but not the future. Given this relentless march toward disorder, the universe we see today, with its intricate structures like galaxies, stars, and living organisms, presents a paradox. How can so much order exist? The answer lies in the universe's starting conditions. The Big Bang was not a chaotic explosion in the conventional sense. It was a state of incredibly low entropy. The early universe was a hot, dense, and remarkably uniform soup of particles and energy. This uniformity was a state of very high order, or low entropy. All the energy was smoothly distributed, not clumped up. Because the universe started in this highly ordered state, it had a vast potential to become more disordered. The subsequent evolution of the cosmos, including the formation of all its structures, can be seen as a consequence of this initial low entropy. Gravity pulls matter together, forming stars and galaxies. This might look like an increase in order, but it is actually an increase in entropy. A smooth gas cloud has low entropy. A star surrounded by empty space has high entropy because there are far more ways to arrange the particles in that clumpy configuration. The process of forming structure increases the overall disorder of the universe. Life itself is a process that creates local pockets of order. An organism is a highly ordered system, but it achieves this order by consuming energy like sunlight or food and expelling waste heat and disordered products into its environment. The overall entropy of the organism plus its environment always increases in accordance with the second law. The existence of any complex ordered system from a star to a human brain is only possible because the universe as a whole is still running down from its initial highly ordered state. The low entropy of the Big Bang is the ultimate source of all the order and complexity we see. If the universe had started in a state of high entropy, a state of thermal equilibrium, nothing would ever have happened. It would have remained a featureless, static soup forever. The question of why the universe began in such an unlikely low entropy state is one of the deepest mysteries in cosmology. Roger Penrose has proposed his conformal cyclic cosmology in part to address this. The anthropic explanation is that only a universe with a low entropy beginning has the potential to create the kind of complex structures necessary for life. We are here because the universe was wound up at the beginning, and we are living through the slow process of it unwinding. Number 1. Quantum rules allow for stable, complex matter. At the most fundamental level, the world is governed by the strange and counterintuitive laws of quantum mechanics. Several of these laws seem perfectly arranged to allow for the existence of stable, complex matter, the kind needed to build a universe with chemistry and life. One of the most important is the Pauli exclusion principle. Discovered by Wolfgang Pauli in 1925, this principle states that no two identical fermions particles, like electrons, protons, and neutrons, can occupy the same quantum state at the same time. The seemingly simple rule is the reason matter is stable and takes up space. Without it, all the electrons in an atom would collapse into the lowest energy level right on top of the nucleus. Atoms would have no size and no structure. There would be no electron shells, which are the basis for the periodic table and all of chemical bonding. Matter would be a dense, featureless mush. The Pauli exclusion principle is what gives matter its bulk, its solidity, and its rich chemical behavior. It forces electrons into a series of well-defined shells, and it is the interaction of the outermost of these shells that governs how atoms bond to form molecules. Another key quantum feature is the quantization of energy levels. In the quantum world, an electron in an atom cannot have just any amount of energy. It can only occupy specific discrete energy levels like rungs on a ladder. This is why atoms are stable. According to classical physics, an orbiting electron should continuously radiate energy and spiral into the nucleus in a fraction of a second. Quantization prevents this, allowing atoms to exist for billions of years. This quantization is also what allows for spectroscopy. When an electron jumps from a higher energy level to a lower one, it emits a photon of a very specific color or wavelength. This gives each element a unique spectral fingerprint, allowing us to know what distant stars are made of. The value of Planck's constant h sets the scale for all quantum effects. If it were 0, there would be no quantum mechanics, and the classical prediction of atomic collapse would hold true. No stable atoms would exist. If it were much larger, quantum effects would dominate on a much larger scale. The world would be a blurry, uncertain place where the definite positions and properties of objects would be impossible to pin down. The specific values and rules of the quantum realm, the Pauli principle, the quantization of energy, the size of Planck's constant, create a foundation upon which a stable and complex material world can be built. They allow for a vast and varied periodic table of elements, each with its own unique chemical properties. This allows for chemistry, which allows for biology. The anthropic argument is that if the fundamental rules of quantum mechanics were different, a universe capable of supporting observers would be impossible. The very fabric of reality at its smallest scale seems to be structured in just the right way to permit the emergence of complexity on the largest scales.